All right, so let's begin again here. So talked a lot about what's a cyclic group and everything, and to complete this story, we really also need to talk about direct products of groups. Now, the direct product of two groups, it's really just the Cartesian product where you multiply each entry according to the rule for that group. So I've just written it by juxtaposition here. Of course, this could be, if they were both additive groups, then this would be addition, or one could be addition, one could be multiplication. There's lots of choices. And first of all, you should notice that the identity in the direct product, of course, is the it's the vector of the identities forming the groups. And that brings us, of course, to my to our first theorem about the direct product group, and that it concerns the order of the element. This is like pretty cool and super useful, and allows you to solve a wide array of problems. If the order of x and y are finite in the direct product of g and h, x comma y and gh cross h, then that has order. The order of the pair x comma y is the least common multiple of the orders of the elements paired. All right, so here we go. Suppose x is in the group and the order of x is m. Suppose y is in h and the order of y is n. We of course have that x to the m is equal to e in the group G, and y to the n is equal to e in the group H by assumption of the order of the elements that just stated. So if we let the least common multiple of the order of x and y be s, that means that s is a multiple of m and s is a multiple of n, according to some integers k and l. So we can calculate. X comma y to the s is x to the s, y to the s. This is, I guess I haven't proved that in these notes, but you can verify that pretty easily, right? Here I'll just do. Let me just do two right quick here while we're talking. So if I have like xy times xy, well, that's xx yy by definition, right? And that's x squared y squared, and of course on the left hand side we have xy squared. So just a little side comment there, and that it works for 2, it just as well works for s. I suppose you could prove that formally by induction if you wanted to. Anyway, so we have x to the s, y to the s, which of course is km and ln, but by laws of exponents that's x to the m to the k, and that's y to the n to the l. But remember, that's e sub g and that's e sub h. So you have the identity to powers, which of course is the identity, which then gives you back again the identity in the direct product. So that shows that the order of x comma y is at most s, because we've shown that the s power gives back the identity. So we need to show then that it's just s. It's not, not less. And so here's how that goes. Now suppose that x comma y to the j is equal to the identity for some j less than s. Then we'd have xy to the j is x to the j, y to the j is equal to e to the g, the identity pairs here. And that would then of course say that x to the j is e to the j, e sub g rather, and y to the j is e to the h, which would then say that m divides j and n divides j, because that's the order. But if j is less than s, this means that j is a common multiple of m and n, right? And it's smaller than the least common multiple, but that's crazy. Therefore, we can conclude that the order of the element is in fact the least common multiple of the elements paired. Very nice thing to know. Let's see if I've got an example here. I do. So in Z10 cross Z5, we can notice that the x equals to 3 has order 10 in Z10 because 3 is relatively prime to 10, so it's a generator. And y equals to 2 has order 5 in Z5, since again it's also relatively prime to 5, so it's also a generator, which means it has order of the group. And as I said, both 3 and 2 are generators for Z10 and Z5. Thus, the order of 3, 2 in Z10 cross Z5 is the least common multiple of the order of 3 and the order of 2, which is 10 and 5, respectively. So the least common multiple of 10 and 5, of course, is 10. And indeed, you can check that 10 times 3, 2 is 30, 20, which is 0, 0. And indeed, no smaller multiple would yield 0, 0. Indeed, the order of 3, 2 is in fact 10. All right, so let's put this technology to play with a slightly more complicated example. Here it is. How many elements of order 6 are there in Z6 cross Z2? All right, so we would need the least common multiple of x and y to be 6. And notice that the order of x and the order of y, they have to divide the orders of the groups. So that's kind of limiting, right? That means that you can have 6 or 3 or 2 or 1 here. You can have 1 or 2 here. So of course we can have order of x is 6, order of y is 1, order of x is 6, order of y is 2, order of x is 3, order of y is 2. All of these give you a least common multiple of 6. So there's 3 cases. Case 1, well, how many elements of order 6 are there? There's 2 elements of order 6 in Z6. And of course there's only one identity in Z2. So that gives you 2 choices. In fact, here they are. 1, 0 and 5, 0 fit the bill for case 1. Case 2. Case 2, again, we have 2 choices for elements of order 6 in Z6. And we still just get 1 element of order 2, namely 1. So that gives you the pair 1, 1, 5, 1. As a funny note here, if you look at my 2015 notes, I missed this case, so I thought there were just 4. But I'm notoriously bad at these kinds of case counting arguments. But so just beware. I'm trying to do my best. I've worked this out carefully. But you know, if you think something's wrong, you know what they say: if you see something, say something. So anyway, case 3. There are 2 elements of order 3 in Z6, and again there's just 1 element of order 2 in Z2, namely 1. So that gives you the pair 2, 1 and 4, 1. So there you go, 1, 2, 3, 4, 5, 6. There are 6 elements of order 6 in the direct product of Z6 cross Z2. So there you go. And that also illustrates that multiple. Remember we said how many elements of order phi d? Well, phi of 6 is 2, and notice that we have 3 times 2. We have 3 times 2, 6 elements of order 6 in Z6 cross Z2. Of course, that also goes to show you that, of course, that's not a cyclic group. Because why? Because we have 6 elements of order 6. Right, and we would just have 2 elements of order 6 if it was cyclic, I believe. All right. Moving along here. Another example. Oh, so many examples. Now this one actually I think is one of your homework problems, truth be told. How many distinct elements of order 10 in Z100 cross Z25? And then we'll ask the additional question, how many subgroups of order 10 are there in Z100 cross Z25? All right, so you ask the question, how can I get a least common multiple of 10 taking, the least common multiple of orders of elements from Z10 and Z25? Well, remember the order of elements of Z10, 100 and Z25, they can only divide 125. So like you can't have an element of order 7. You can't have an element of order 11. That's just not possible because those don't divide 125. So your choices are somewhat limited. You can have order 10, order 1, order 10, order 2, order 10, order 5, order 2, right? Except actually case 4 is not even a possibility because I can't have an element of order 2 in Z25 because 2 does not divide 25. So actually case 4, nonsense. You can just cross that out from the start. There really are just 3 cases. So we really only have to consider cases 1, 2, and 3. Now case 1, the order of x is 10, Well, phi of 10 is 4. There are 4 elements of order 10 in Z100. And how many elements of order 1? Well, there's just one identity, so that gives us 4 choices for case 1. And case 2, again, the order of x is 10, the order of y is 2. Well, there's just one element of order 2, so that gives us another 4 choices. Case 3 here, we have excuse me. Case 3, the order of x is 10, and the order of y is 5. Well, that's more interesting. 4 choices. Phi of 10 is 4. Phi of 5 is also 4. So we have 4 times 4, 16 choices in case 3. Altogether, we have 4 plus 4 plus 16. That's 24 elements of order 10 in Z100 cross Z25. This is how we can count them. Now, returning to the question, how many subgroups of order 10? Well, each cyclic subgroup of order 10 has 4 generators. We found 24 generators. So 24 divided by 4, this gives us 6 subgroups of order 10 in Z100 cross Z25. This example, I believe, is from Abelian, actually, and he likens this problem to counting sheep by counting the number of legs. You know, if you got a sheep pen and you count 100 legs, you got 25 sheep, right? Well, modulo some unfortunate genetic deformity or something, but yeah, this is how we. So I when I taught abstract algebra before, I had a zoology major, and I used to try to come up with examples that would illustrate other other number of leg counting. So if you could find a what number has 8 generators, you could think about that like counting spiders or something, you know. All right, I'll shut up. Page 20. A theorem. This theorem's very, very helpful, simple to remember, and really guides our thoughts a lot. If G and H are finite cyclic groups, then G cross H is cyclic if and only if the order of G and the order of H are relatively prime. So here's the proof. Suppose G and H have order m and n respective that are relatively prime. So observe that the least common multiple in that case is just the product of mn. So if we assume that G is generated by A and H is generated by B, where the order of A is m and the order of B is n, then the order of the element, the pair A comma B, is the least common multiple of mn, which is equal to mn. However, also just by counting, the size of the direct product of G and H is mn. So that means that A comma B serves as a generator because it is as big as the group. The subgroup generated by it is as big as the group, which means it covers everything by counting. And we find, of course, then that G cross H is cyclic. All right. Conversely, suppose that G cross H is cyclic and that the order of G is m and the order of H is n. Let D be the greatest common divisor of m and n. Okay, so suppose x and y is a generator. We can do that because we assumed it's cyclic. And that the subgroup generated by x comma y, of course, is G cross H. Notice then that x to the m is equal to e and y to the n is equal to e because the order of G is m and the order of H is n, and x and y are elements of the group. So of course any element to the power of the group, any element to the order of the group is the identity. Prove that. And hence xy to the mn over d, by usual properties of exponents, it's x to the m to the n over d, and x to the y to the m over d. But that's e and e, which is ee. Thus, the order of xy, which we said was mn, is less than or equal to mn over d, because we just showed that n over d goes to the identity. And thus, that implies that d equals to 1, right? So the greatest common divisor of m and n is 1, which is to say that they're relatively prime. Corollary. Zmn is isomorphic to Zm cross Zn if and only if the greatest common divisor of m and n is 1. So the proof is, pretty simple. If the greatest common divisor of m and n is 1, then Zm cross Zn is cyclic of order mn by theorem 2.7.10, which we just proved. then by the uniqueness of cyclic groups of a particular order, we find that Zmn is isomorphic to Zm cross Zn. And conversely, we can apply the theorem 2.7.10 to get the other direction there. All right, so these results hold for two things, but they also hold for more things. Should mention, we can talk about the direct product of K groups, just the same, and in that case, the if you have n elements of, well, now I'm talking about n product of n things. I had K things up here, now I'm talking about n things, whatever. So if I have n elements of finite order, and I look at that tuple formed by those n things, and the direct product of those groups, well, that has order which is given by the least common multiple of all these guys. So works just the same when you've got more than two. And here's an example: 2, 3, 4 in Z3 cross Z10 cross 11. Well, the order of 2 is 3, the order of 3 is 10, and the order of 4 is 11, because 2, 3, and 4 are relatively prime to 3, 10, and 11. Right? In fact, 2, 3, and 4 could all serve as generators of their respective groups. Anyway, the order then of 2, 3, 4 in this context is the least common multiple of 3, 10, and 11, which is 330. 2, 3, 4 is a tuple such that you will not get back to the identity, you will not get back to 0 until you take and add it to itself 330 times. That's pretty cool to figure out with this little calculation. And of course that also brings us to another theorem, which is that if you have Z sub n1, n2, nk, where these are all relatively prime, pairwise prime to each other, pairwise relatively prime, then that's isomorphic to the direct product of Zn1, Zn2, all the way to Znk. Again, the condition here is that these, the numbers forming this product have to be relatively prime. GCD ni and j is equal to 1 whenever I is not equal to j. So, for example, Z3 cross Z10 cross 11 is isomorphic to Z330, and Z2 cross Z3 cross Z7 cross Z11 would be isomorphic to Z462. Incidentally, that also shows that this group and that group are cyclic groups, respectively of order 330 and 462. So when you see something as a direct product of groups, the jury's not out whether or not that's cyclic. You have to do further investigation. It may or may not be possible to collapse it down to just one Zn. So, classification of finite abelian groups. I think I've asked you a question or two about that in the homework, and let's talk about the result. Every finite abelian group, remember that means the group operation commutes. Finite means it has, well, finitely many elements. Well, anyway, every finite abelian group is the direct product of groups of prime power order. Moreover, the number of terms in the product and the orders of the cyclic groups are uniquely determined by the group. So that's a huge result. Really, that's something that is naturally proved in the theory of modules, and like a larger discussion of linear algebra of rings and such. So maybe some future course or independent study I can do with you if you're interested in that. But I don't think we really get into that in this course, of course, because that's really kind of abstract algebra 2. But anyway, here's an example. How many types of abelian groups of order 100 are there up to isomorphism? Well, 100 is 2 squared times 5 squared, right? 4 times 25. Hence, well, there are different cases, right? You could have Z4 cross Z25. Now 4 and 25 are relatively prime. So in fact, this is the cyclic group of order 100. In contrast, you could also have other ways to break up the prime powers. You could have Z2 cross Z2 cross Z25. For what it's worth, that's the same as Z2 cross Z50. I don't believe this is, this is not cyclic. Well, there is a unique cyclic group, right, of order 100. This is it up here. So these are not. but you could have Z2 cross Z2 cross 25. You could have Z4 cross Z5 cross Z5. Or you could have Z2 cross Z2 cross Z5 cross Z5. These are 4 distinct non-isomorphic examples. If you study these different cases, there are different numbers of elements of different orders. They have different structure as groups. They all have order 100, and these are the only possible up to isomorphism kinds of groups, Abelian groups of order 100 you can have. But there it is. All right. I think I might have another example. No, I think I stopped there example-wise. I hope that's enough to get you wet your whistle. You can come talk to me about it in office hours if it's not enough, or email me, whatever. I do think I have a few more examples in the notes. Well, I mean, not really. Not really. It's pretty much that. But it's not... it's really not... You just have to look at the prime power factorization, right? All right, so this brings us finally back to what I've been teasing about for a while, which is the structure of UN, all right, and Euler's totient function, etc. We have noticed before that phi of a prime is p minus 1, and that phi of a prime power is the prime power minus 1. And our proof of that was basically just counting the relatively prime elements forming U of pk, and we derived the result above in that previous class, right? Now, there's another theorem that gives us further insight as to the structure of the group of units. Here it is, right? Here it is. Theorem. Suppose that the greatest common divisor of S and T is 1. S and T are relatively prime. Then UST is isomorphic to US cross UT. Corollary. If the greatest common divisor of S and T is 1, then phi of ST is phi of S times phi of T. So this is really, really nice because it allows us to calculate the Euler phi function when we're looking at the Euler phi function formed by relatively prime pairs product. This is also known as the multiplicative property of the Euler's totient function. And this is just so important to calculations. So important. Really, really important. Now, the proof of this theorem is pretty straightforward, but a little bit technical, and it basically just rests on writing down a formula and proving that formula in fact does give an isomorphism. One of the critical calculations that we'll see is that we need what's called the Chinese remainder theorem, and that's what we'll talk about next. But let me just get to it here. So we consider the map, and so here I'm doing modulo st versus modulo s versus modulo t. They're all in play. So psi of the equivalence class of x mod st is mapped to the pair equivalence class of x mod s, comma equivalence class of x mod t. So this is a claim right here. I haven't shown that yet. And so for each equivalence class x st in UST, we make this definition, and we're going to assume that s and t are relatively prime. Now, first of all, we need to prove that psi is thus is thus defined as an isomorphism, right? And since we're dealing with equivalence classes, we should try to verify, first of all, that psi is single-valued, right? So suppose that x and y are both representatives of the same equivalence class, mod st. Then y is equal to x plus some multiple of st, say j multiple. And then we can calculate psi of yst is equal to this, but y is equal to x plus jst and x plus jst. And of course we can factor out the s, we can factor out the t, and then by the properties of modular arithmetic mod s and mod t, we can collapse this down to just x and x, mod s mod t, which then of course takes us back to psi of the equivalence class of x mod st. This proves that psi is in fact single-valued, that even though I used representatives of the coset to define it, in fact, there is no dependence on that choice. It's a single value. It's a function. Now, we should also prove that this claim right here, in fact, that psi is into us cross t. I mean, I can claim it's into. That doesn't mean it is so. It remains to show that this pair actually is in here, right? And so I know that's a subtle thing, and we often don't really get into it for examples, but it matters here. And it's pretty simple to prove, though. So suppose this has an inverse. Well, that means that there is x times y mod st is 1 st, right? Which means that that multiplies to xy minus 1 has to be a multiple of st. And thus, xy minus 1 is equal to nts, and x minus 1 is nst. Well, that shows that y actually serves as the inverse mod s, and it serves as the inverse mod t, which is to say that xy is 1 and xy is 1 mod s and mod t, which then shows that psi is into. Continuing the proof, we still haven't proved it's a homomorphism. All right, so let's get to it. So here's our definition. Is it a homomorphism? Well, look at the product of x and y. By definition, that's psi of the product xy mod st, which then by the definition of psi is this, which then by properties of modular arithmetic, that's xy mod s times the equivalence class of x mod t, equivalence class of y mod t, which then by the properties of the by multiplication of the direct product is the pair xx times the pair yy mod s mod t mod s mod t, and then that's psi of x and that's psi of y again, which proves that this is a homomorphism. It preserves the operation. Now furthermore, since ust and us cross ut are both finite, to show that psi is a bijection, we can either show it's onto or it's injective. Recall psi is 1 to 1 as a group mapping if and only if the kernel is just containing the identity. Therefore, we can just calculate the kernel. Well, what's the kernel? The kernel of psi is equivalence classes mod st such that x is equal to 1 and x of t is equal to 1, right? So we have to solve two congruences at once. We have to solve x congruent to 1 mod s, x is congruent to 1 mod t. Well, good news. The Chinese remainder theorem provides that the solution, the unique solution to this, in fact, is x is equal to 1 mod st. And so, therefore, the kernel of psi is just the set containing 1, which proves that psi is injective, which completes the proof that psi is, in fact, a bijective homomorphism, and thus it provides the isomorphism of ust with us cross ut for relatively prime s and t. So, now, I talk about the Chinese remainder theorem as if it's something you know what it is. That may or may not be true, actually. Maybe you saw it in a previous course, maybe you didn't. I do have a homework problem which requires you to use it. So I think it would be good for us to talk about what is the Chinese remainder theorem and how it's proved. Because the proof here is constructive and actually not that complicated. So here goes. Now I'm going to state the Chinese remainder theorem for R congruences, but I think I have an example for 2 and for 3 for what it's worth. Anyway, suppose you have M1 through MR. They are pairwise relatively prime, and we have this system of congruences that we're trying to solve. X congruent to A1 mod M1, X congruent to A2 mod M2, X congruent to AR mod MR. So we're trying to simultaneously solve this system of congruences with respect to these various moduli. Well, the theorem says that there's a unique solution modulo M, which is the product of the moduli. Alright, so here's the proof. Begin by constructing the solution. We define big MK as M over little mk. Now big M is this product right here. So for each, we define big M sub k, M over little m sub k for each k from 1 to R. Now notice that the greatest common divisor of big MK and little mk is 1 because of the construction of big MK. See, we're dividing out, this is a hat you don't want to wear, it means it's not there. We're dividing out the MK factor, right? So like there is no common factor between this product of M1 through MR and MK because we've deleted the MK factor. So that's why big MK is relatively prime to little mk. Alright. So we can apply Bezout's theorem and select yk and bk for z for which ykmk plus bkmk is equal to 1 because again big M and little m sub k are relatively prime. And then, so we can observe from that equation that YK is congruent to 1 mod MK. And then, by math magic, we can construct the formula like so. So we say X is equal to A1 M1 Y1 plus A2 M2 Y2 plus da, 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 AR MR YR, where the where the A's are given in the initial problem statement, the M sub, the big M's we constructed, and the Y's are described here by this boxed equation. Really, the Y's are the inverse of the big MK's mod the little MK's. So that's what you're looking for. You're looking for the inverse. Y is really the inverse mod little MK of big MK. We'll see that in the examples. I'm just saying that there. Anyway, and then, so here's the proposed solution, and you can check then that this has M sub j. Notice that M sub j is congruent to 0 mod M sub I for each I not equal to j. Because of the construction, it's got a copy. It's a multiple of M sub I, for every I not equal to j. And so it's congruent to 0. And hence X is congruent to AI, MI, YI. Everything else drops out, mod MI. And so, but again, MI, YI is congruent to 1 by this up here. And so we get AI. But I was arbitrary, hence X solves all the congruences. And finally, if Y was another solution to the congruences, then X is congruent to Y is congruent to AI for all I, which means that MI divides Y minus X for each I, and consequently M divides Y minus X, which shows you that the your second solution would be congruent to the first one we constructed, mod M. So it's unique. The solution is a unique mod, the big M. All right, so let's actually look at an example. I'll try to stop coughing. If we're solving X congruent to 2 mod 3 and X congruent to 7 mod 11, in terms of my notation, A1 is 2, A2 is 7, our big M is 33, our little m1 is 3, our big M1 is 33 over 3, which is 11, our little m2 is 11, our big M2 is 33 over 11, which is 3. So, mod 3, big M1 inverse, 11 inverse is 2. You can check that out, right? Like 2 times 11 is 22, which is 1, mod 3. And mod 11, 3 inverse is 4, because 3 times 4 is 12, which is 1 mod 11. So there's your Y1 and your Y2. Now you put it together. X is equal to A1 M1 Y1 plus A2 M2 Y2, which in this case is 2 times 11 times 2 plus 7 times 3 times 4. And that gives you 44 plus 84, which gives you a 128. And then subtracting off copies of 33, that brings you back down to 29. So X is equal to 29 mod 33. That is the unique solution to this system of congruences. And you can check it, right? X equal to 29, well, that's congruent to 2 mod 3, and X equal to 29 is in fact congruent to 7 mod 11, because of course you subtract off 22, you got 7, you subtract off 27, you got 2. So this 29 simultaneously solves both of these congruences up here. This is the Chinese remainder theorem. Now, I thought it would be good to have another example with 3 things, so here it is. 3 things. If I want to solve X congruent to 3 mod 3, X congruent to 7 mod 8, X congruent to 10 mod 11, well, what I face is A1 is 3, A2 is 7, A3 is 10. My moduli, M1 is 3, M2 is 8, M3 is 11. So then I form my big M's. First of all, the product of the moduli is 264. My big M1 is, big M divided by 3, which is 88. Big M2 is big M divided by 8, which is 33. my big M3 is my big M divided by M3, little m3, which is 24. So you need to calculate inverses of these modulo 3, 8, and 11 respectively. Now we could use the Euclidean algorithm because we know we can calculate inverses in like Zn using the Euclidean algorithm, but but I just went ahead and skipped those calculations. Forgive me. This is already getting kind of long. Let's see here. So, make sure I got it all on here. 88 inverse is, well, mod 3, that's the same as minus 2 inverse because I can subtract 90, you know? And then minus 2, well, that's silly. That's just 1 inverse. This is, okay, so 88 is, I believe 88 is actually 1 mod 3. So y1 is 1. 33, again, kind of embarrassing. That's 1 mod 8, so it's its own inverse. Y2 is 1. 24 inverse mod 11, well, that's subtract off 22, that's 2 inverse. 2 times 6 is 12, right? So that makes 6 the inverse of 2 mod 11. So finally something interesting, y3 is 6. Put it all together. A1, M1, Y1 plus A2, M2, Y2 plus A3, M3, Y3. Well, A1 was 3, M1 was 88, Y1 was 1, A2 was 1, M2 was 33, Y1 was 1, A3 was 10, M3 was 24, Y3 was 6. So the first one gives me 264, which, since we're doing the calculation mod 264, that just drops out. And then this has got 231 and 1440. Add those together, you get 1671. So what I did then to figure out what to do next is, like, it's pretty simple, guys. You just do like 1671, right? And divide by 264, right? What's that give you? That gives you 6.32, blah, blah, blah. So that told me to take 1671 and subtract 6 times 264. That will give me a number which is congruent to 1671 mod 264, right? And that's why I subtracted off 6 copies, because I knew that would get me to a small number which was congruent to the 1671. I mean, yeah, okay, fine. You could leave your answer as 1671 mod 264, but that's just tacky. So anyway, 87 mod 264 is the answer. And you can check that 87 is congruent to 3 mod 3. 87 is congruent to 7 mod 8, right? Because you can subtract off 80 and you get 7. And 87 is congruent to 10 mod 11 because 88 is 87 is minus 87 minus 77 is 10. So it checks. We've solved all 3 of these pesky congruences at once by using 87. This is the magic of the Chinese remainder theorem. Some examples. So we got this lovely theorem. Let's try to put it into practice. You excuse me. U200 is 25 times 8. So 25 and 8 are relatively prime. So that is U25 cross U8. But U25, of course, is oh, see here, I'm sorry guys, I'm using some, I kind of jumped the shark a bit here. This is the theorem, like u to the 2n is z2 cross zn minus 2. So like u8 is z2 cross z4 actually. Wait a minute, let me think about that. 3 minus 2. I guess it, no, u8 is z2 cross z2. I think it's the Klein-4 group. But anyway, this theorem here on page 29 actually guides my explanation for what u to the particular prime power is. So anyway, u8 is in fact isomorphic to z2 cross z2, and u5 squared is z20 up to isomorphism. So u200 then is z20 cross z2 cross z2. So, you know, let's smell the roses here for a second. If I had a triple in this, notice that the order is the least common multiple of the orders of the elements paired. So that has to be, well, you can have at most 20, you can have at most 2, and you have most 2, so check it out, that's the least common multiple of those is 20. That means that the highest order element in U200 is 20, because order of elements is preserved under isomorphism. Right? So if I understand what are possible orders of elements in this Cartesian product, it tells me what's possible order of elements in the group of units of order 200. In fact, you can't have modulo 200 a unit which has order higher than 20. That's what this proves. All right, here's another example. U405, well, that's 5 times 81, which is 3 to the 4th. So 5 and 3 to the 4th are relatively prime, which means that this is isomorphic to U5 cross U to 3 to the 4th. And then, well, U5 is 5 is prime, so that's Z4. And 3 to the 4th, well, that's 3 to the 4th minus 3 to the 3rd. So what we have is Z4 cross Z54. That's what the decomposition of the group of units of 405 is in terms of direct products of modular modular integers. And again, this is super useful because we can analyze possible order of elements here very simply, whereas here, if you ask me like, oh, how many elements of order 10 are there in U405? Goodness, I don't know, but I could figure it out from over here, U195, well, that's 5 times 3 times 13, those are relatively prime. And so we get U5 cross U3 cross U13, which is Z4 cross Z2 cross Z12. Easy peasy. And now, one of your homeworks, I have asked you to prove that the automorphisms of Zn is isomorphic to Un. And that's pretty neat because once you prove that, then you can figure out things about the order of automorphisms, right, of a particular order by studying how many elements of that particular order are in Un. Well, how can you do that? Well, you can do that for Un because you can break Un into a product of, cyclic groups. And so we have tools for studying the order of elements in such products. And so that's the game plan there. It's kind of sneaky, but that's it. Now, this, I should mention, of course, it also holds for more than two things. If you have your R things, they're relatively pairwise, relatively prime, then it's isomorphic to the direct product of those R full things. This proof basically says it's the same proof. It still works. Essentially all the steps go through when you have more than two things, and it just comes down to using the Chinese remainder theorem to prove that the kernel is just that one thing. So essentially the same proof. And then the corollary, of course, is that if you have the Euler phi function of a product of relatively prime product, then it's the product of the Euler phi functions of the factors forming the product. And so this pretty much tells us how we can classify Un. If n is the product of prime powers, as any integer is, right? There's a unique fundamental theorem of arithmetic, right? There's a unique prime power factorization of every integer, and so you can get those p1 through ps's, and then Un is going to be the direct product of isomorphism of up to the k1, p to the k2 dot p to the ks, and then what those actually look like in terms of Zn is given to us by this little theorem right here. Namely, like for even's a little bit weird. U2 is isomorphic to 0. I mean, U2 is a trivial group. U4 is Z2, and U to the 2n is Z2 cross Z to the 2n minus 1. For example, U to the 3, U to the 8 was Z2 cross Z2 as an example. And then for odd primes, it's easier. It's just odd primes give you a cyclic copy, just straight up Z to the Pn minus 1. So, in short, this allows us to break Un into a product of copies of Zk as appropriate, and it reveals the structure of the group of units mod n. Alright, now, last but not least, we can talk a little bit about here about Fermat's little theorem. Now this actually isn't Stillwell, of course. If p is prime and a is non-zero mod p, then a to the p minus 1 is equal to 1 mod p. Excuse me. So let's see here. Well, we'll see examples of this when we do the RSA calculation, I suppose. But anyway, so here's the proof. ZP has p elements, and for p prime, the order of the group of units is p minus 1. So if you have a subgroup generated by A in UP, then by Lagrange's theorem, the order of A has to divide p minus 1. Thus there exists n in the natural numbers for which p minus a is a multiple of the p minus 1 is a multiple of the order of A. And so modulo p, we can calculate that a to the p minus 1 is a to the n times order of A, which is a to the order of A by definition is 1. So excuse me. We have 1 to the n is equal to 1. Let me see here. I guess I owe you an example, perhaps. Let's see here. So like, all right, let's see here, like p is prime. So let's think p equals to 17, right? And let's see here, a, well, we could do a equals to 10. A equals to 10, right? That's not congruent to 0 mod 17, right? Then Fermat's little theorem says what? It says that a to the p minus 1 is equal to 1 mod p. Now that specifically for the numbers I've just chosen says that 10 to the 16 power is equal to 1, congruent to 1 mod 17. So yeah, you know, Fermat's little theorem doesn't seem so little when you actually put some numbers in, does it? Not at all, really. Not at all. I mean, goodness gracious. 10 to the 16 is huge. To know that that's congruent to 1 like that with no calculation, I mean, dang, that's a pretty weighty little observation. And we'll use that in the RSA calculation, if I recall correctly. So, upcoming. Euler's theorem says that if you have x in the group of units of order k, then x to the phi k is equal to 1. So really this is just the statement that you're taking a group element, you're raising it to the order of the group. So of course you have to get back the identity. That's one of our properties of a group. Any element of a group raised to the order of the group gives you back the identity. That's a straightforward consequence of the theorems we've looked at. And so there's the proof. Now, so let me just take a gander at your homework with you. Here it is. This was mission 2, right? So my printer's a little sketch. Sorry about that. But basically problem 13, problem 14, problem 15, problem 16, even problem 17, like these are all just modular arithmetic questions that really go back to the lecture when I was still healthy. If x and y is in 2z, prove that the GCD of x and y is also even. I forget how to prove that, but I don't think it's that complicated. Prove the cube root of 5 is irrational, so you know, suppose otherwise, and you can come to a contradiction, I believe. And that has to do with, like, well, anyway, I did something similar to that in the lectures. Find the remainder of 6 to the 13 upon division by 4. You know, whenever you're trying to find the remainder of some giant number using division by 4, I'm thinking about modular arithmetic mod 4. Like, that's the way to solve that kind of problem, right? Here's a Euclidean algorithm problem. Here I'm stating Fermat's little theorem, which I just proved for you, and so I've encouraged you to use Fermat's little theorem. So you can actually calculate the inverse using Fermat's little theorem, right? So this instructs you to do that. And then there's two different strategies, right? You could use Fermat's little theorem to calculate the inverse, or you could use the Euclidean algorithm, a la Bézout and all that, to calculate the inverse. You got choices. And similarly, problem 23 intends to help you to understand more how Euler's theorem is also similarly useful, and to contrast that to using the Euclidean algorithm for your computation. And then I've assigned exercise 3.5.1 on page 55, which I don't know where my book is. Sorry guys, I don't have anything to say about that. Now, mission 3. I assume that this was something easy to get started. I said it is, so let's trust me. Find the solution set for this equations in Z. So follow my hint. Page 34 of Stowell gives you an algorithm for solving such things. I haven't covered that in lecture, but it's actually pretty straightforward. I will write out the solution for you, so that'll be my instruction in on that point. Now to solve problems in Zn, if we can find the multiplicative inverse of like 3 or 12, and then we can solve for x. So like I think 27 is actually easier than 26, despite the fact it's kind of a little more abstract. Now problem 28, that's just straight Chinese remainder theorem problem. So you can follow the example, I hope, that I gave you. Don't be scared by all the words here. I'm just basically explaining to you the concept of evaluation mod Zn of a polynomial given to you over with coefficients in Z. And ultimately down here is the actual problem. Show that this has no 0 in Z by showing that F4Z has no zeros in Z4. Actually, all you have to do is plug in equivalence class of 0, equivalence class of 1, equivalence class of 2, equivalence class of 3. And if you can show all of those don't output 0, well then by this discussion that explains that in fact F has no integer zeros. So this is a important idea in terms of showing that there don't exist. You can show that there don't exist integer solutions by checking, modulo a particular residue. Excuse me. Problem 30, find copies of Zn for which Un is isomorphic to the direct product for what? U33, U40, U12. I hope that these problems are not mysterious now that after you suffer through my lecture here. Find the number of elements of order 10 in Z100 cross Z25. I actually literally worked that out in this lecture. How many cyclic subgroups of order 10 are there? I actually worked that out in this lecture. What are the possible abelian groups of order 108? Well, you got to look at the prime power factorization of 108 and the different possible ways to break that out. I think that's also actually example 3.3.29 on page 99 in my notes that I posted for you guys. Problem 33, I say show that the automorphism of Zn is isomorphic to Un. So, this one you're going to have to think about a little bit. How many automorphisms of Z68 have order 4? Well, so you're asking the question, what's the structure of U68? And you can figure out then how many elements of order 4 are there in U68, because problem 33 showed you that Z68 is isomorphic to U68. But we know how to break down U68 in terms of the structure theorems I showed you. And then finally, problem 35 is kind of more fun. F of x is mx plus b. Use the alphabet code, a equals 0 all the way to z equals 25. I give you a message. I tell you the message that cat is encrypted to kedge. So this data should allow you to figure out what the values are for m and b, right? So I say find M and B, and then decode my message to you, Red Maju. So this will be unsurprising after you find the solution. And then finally, I've asked you to do exercise 4.4.1 on page 73. Again, I still owe you 37, 38, 39, and 40, I guess. Hopefully on RSA, and I'll try to make those problems short and instructive. But anyway, that is it. That is it for that part of the course. We'll pick up Monday with RSA, and look forward to seeing you in person. Thanks.